Welcome to my Physics 2 Lab 5 final lab. We start off with our equation slide so we can see our magnetic force equation. This is generalized, so it can be used whenever the magnetic force is perpendicular, parallel, or neither. We used a dipole moment of a dipole and a r hat, so that would be a normalized distance to find it. And then we also have our flux calculations, or specifically our flux over time calculations, and the magnitude of our magnetic force here as well. And we also have our velocity and position change over time, as well as the sum of our forces. But all of this, of course, has to have a purpose. So why are we doing all this? We're looking to see how physics resists changes in flux by slowing down a falling magnet. So we're going to have a magnet with a north dipole and a southern dipole, and it's just going to fall down a pipe, and we're going to time that to see how long it takes, because normally it would be actually quite quick, but it will go a lot slower because of the fact that, again, physics resists changes in flux, so that resisting of change will also increase our time. So our system is going to be the magnet and aluminum foil pipe, and our surroundings are everything else, and this is our final result, 1.599 seconds. Let's see how accurate that is. So I have a little drawn out of the lab. So this is sort of how we dropped it in. Now, we don't know whether or not it was north and south, but arbitrarily it should be the exact same. So here are our measurements for the pipe, and we dropped it down with the same sides facing the same directions every time. And these were the times that we got. 1.44 seconds was the average, so not far off of what we found from the coding. So let's go ahead and look at that coding right here. So we have some of our constants, some of the setup for the lab as well. And then over here, as you will notice, we release our magnet from rest at time 0. And as time moves on, we need to calculate how our flux is changing, for example. So we do that with this equation right here. So this will have our numerator and our denominator of df dt, which the equation was on that second slide. So we obviously, of course, have our force of gravity, which is going to be added to our magnetic force, and then we're going to have some velocity and position update down here. We're going to find the flux using that function on that last slide. We're also going to find the current. We're going to use a different function to find our magnetic force on the ring, which is sort of the ring created by the aluminum foil at whatever position we're at. So like, for example, down here, we'd have a little ring of foil right there. And then we have all of this to find the magnetic force on the ring, which again we can find using our equation from that second slide. And then updating that with our magnetic force on the magnets. So as you can tell, flux is pretty steady. Our velocity is pretty steady right here, and then it kind of drops off once we've landed, and the time again wasn't actually far off from reality. So overall, what would happen if the resistivity of the conductor was as close as possible to 0? Well, a higher resistivity would mean a lower current and a lower force, so therefore a lower resistivity as it goes to 0 would mean a higher current and a higher force. And if there were holes or slots cut into the tube, it would sort of be like dropping that magnet through thin air. We wouldn't have a flux in that specific area. So we would need to calculate for the rings either only really acting in certain areas rather than being an actual ring, or if it were just sort of like falling between two disconnected tubes, but then we would have to take it into account that it's just falling through air at some point. But overall, that would be the end of my presentation. Thank you for watching.